Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Boyle Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Praveen Tammana, and he will be speaking on validating and securing P4-based programmable data plane systems. Dr. Praveen Tammana is currently an assistant professor in the Computer Science Department, IIT Hyderabad. His research interests are at the intersection of systems, networks, and security. His current focus is on designing and building network systems that make networks easy to manage, secure, and robust by using exciting emerging technologies such as software-defined networking and P4-based programmable data planes. Prior, he was a postdoctoral researcher at Princeton University, USA. Dr. Praveen has received his PhD from the University of Edinburgh, UK. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Praveen directly or type them in the chat box and we will moderate it with him. Over to you, Dr. Praveen.
Thanks for the kind introduction. In the next 1 hour, I'm going to talk about what are programmable data planes and how are they related to OpenFlow, and also how are they different from OpenFlow systems, and followed by why it is important to validate systems that are built on top of programmable data planes. And finally, I'll conclude with some of the potential research opportunities in the security space, where securing these data plane systems is becoming very important, especially when they're deployed in real world. So let me get started with first just to give you a quick recap on what is SDN and how it is different from traditional networks. To give you a quick summary, SDN is a new approach to networking. It's not about a protocol and architecture like TCP, IP, but it's about how you design network control, how you design network control, and you program the system so that you meet the routing and traffic engineering requirements. And it did so by separating using two simple concepts. One is clear separation of a decoupling control plane and data plane, and a standard API or open API to directly interact with the data plane. So while SDN doesn't do much, but it enables a lot. To be more specific, if you look at the traditional networks, you have a control plane distributed algorithms that are running in the control plane, and it would be listening to network events like topology changes or advertisements, network events, and listen to these algorithms, listen to these advertisements or events, and modify state or establish state in the network devices. Whereas the software-defined networking, the idea is to decouple the control plane and the data plane, where you expect more sophisticated operations being running in the control plane that is logically centralized, and it is considered to be smart, whereas the switches would be left to the term where mainly the function is to forward packets as per the instructions that are given by the control plane. And to interact with the data plane, the API to talk to the data plane, that is one of the popular protocols, is OpenFlow. But actually, the switch vendors do use different protocols between controller and switch data plane. And to be more specific about what exactly the OpenFlow is, it's about two things. One is a protocol to interact with the switch so that you could update table entries or query network statistics using that protocol. And another aspect of OpenFlow is an clean abstract match action abstraction, so that the different control plane applications would program the switch data plane based on this match action abstraction. The idea is that the packets would the data plane would process packets by matching on different packet header fields and take action, appropriate action. Some example header fields that has been commonly used in OpenFlow are typical source Ethernet, destination Ethernet, and IP source IP, destination UDP TCP port. And for every flow rule, flow entry in the data plane, you also have you can also have a byte counter and keep track of number of packets that hit particular flow entry, and also an associated action that are, if you look at today's OpenFlow, there are about more than a dozen actions that include modifying packet header fields, forward, drop, or encapsulate and forward to controller. So far good, but why do we need data plane programming? And what are the issues with OpenFlow? So while it did change the way how we program the networks, but there are still some limitations or issues with it. One is if you look at the evolution of this OpenFlow. So especially whenever new network requirements come, you perhaps want to deploy a new protocol that requires to be matched on different header fields. Where initially when OpenFlow standard was designed, there were only 12 header fields, and subsequently it went through multiple versions, and now there are up to 40 different match fields. And the main challenge is that the standardization followed by the development of the chips to support or recognize those match fields would take a longer time. So and another issue is that limited interoperability, because today, if you look at the switches, they communicate, they speak to controller in different languages. So one is OpenFlow, but there are other popular protocols like netconf and XML and JSON variants. And it becomes the controller that interacts, that are sitting between these, that is sitting, acting as a southbound, talking to the OpenFlow plane as a southbound interface would become cumbersome, and it has to support a wide range of protocols. And finally, though initially when OpenFlow was designed, there was a fixed set of match fields and a fixed set of actions being considered. But in the recent past, it has been shown that even to make any change to the fixed function ASIC, let's say I want to add, want to recognize new packet header fields or add a new action, then that it would take years, because it has to go through standardization process followed by ASIC development. And moreover, that even if you decide to use new ASICs, then you have to dump the existing fixed function pipeline or ASICs, and then buy these new hardware. So it is also not cost efficient. So given these issues, this led to the rise of P4. But before that, I'd like to motivate some other the example or the design philosophy of OpenFlow. So imagine that you're building a network system, and you may have certain requirements, and you're expecting some features to be supported by the switch ASIC. Then the first thing you do is you go to the market and see which switch ASIC would support or is suitable to as per my requirements, by looking at the spec that is written in English. And then I would find the best switch ASIC, and then I pick that. Once I pick that ASIC, then I am restricted to the kind of drivers that are running on that switch, or the control plane interface to that switch that is also provided by a third-party vendor. So it's essentially following a bottom-up approach. And And tomorrow, if my network requirements or demands changes, then or to enable new feature and new protocol, then it would take at least 4 years. It would take more than 3 to 4 years to enable that new function or new protocol, because it requires changes to the ASIC. And the P4 has followed a different design philosophy, where it took a top-down approach, where you take what the network operators or the network admin wants and instruct the switch to process the packets in the way that the network operators want to, by programming the switching chip using the P4 programming language. And tomorrow, if network demands change, or when you want to enable new protocol or new feature, then you can modify the P4 program accordingly and make changes to the switches to the programmable to the device in a week, within days, overnight, or it could be within a week, but not year. After doing, of course, you supposed to put this program in the data plane after doing necessary testing, and the necessary required amount of testing has to be done before you push the program into the data plane. So this is the very high-level idea of the design philosophy that the P4 programmable data planes follow, language and programmable data planes follow. And some advantages of data plane programmability is you can add new protocols and new features quickly. And you don't need to use unnecessary protocols. If you look at today's commercial boxes, they come up with many protocols that you may not really need. And it oftentimes seen that the unexpected interactions between these unused protocols could lead to failures. So it eventually reduces the complexity. And moreover, since you have more control over how you allocate data plane resources like TCAMs, SRAM, or match action table units, then you could allocate the resources between different network functions like layer 2, layer 3, NAT, or stateful firewall. And that control is now given to the programmer or the network administrator. And since you can process the packets in the way you want, you can collect the telemetry data at line, right? Assuming that you respect the resource constraints, and get the necessary visibility by programming the data plane with the appropriate registers and counters. And moreover, the key idea is that it enables software stack development, where you could rapidly change the data plane, that eventually make innovation faster. And one important thing is that now, since for any new requirements in your network, you don't need to share with the chip vendors or third-party vendors. You can write your own programs, and you don't need to share those programs to the third-party vendors. So that way, it gives you competitive advantage. In short, you think like a programmer rather than design of protocols or standards. And some of the programmable network devices that are out there in different has a different in different environments and different capacities, where typically you have switches like Intel Barefoot Tofino or Cavium XPN, and smart network processor-based SmartNIC from Metronome and NVIDIA enable you to program using P4. Also, there are high-speed software-based packet processing engines like OpenFlow, eBPF, DBVal, PDK, which run on CPU. They are another set of targets for the P4 programming language, and also FPGA-based from Xilinx and Statistons are another target. But each has they fall in at different. They have strict trade-off between the performance of the capacity that you get in terms of throughput versus the latencies and the amount of resources that you allocate. So, and the flexibility that you get in each of these varies from target to target. But in general, it allows these programmable data plane devices would they allow us to allow the network operator or the programmer to tell how to process the packets. And what else you can do with P4? There are a wide range of applications, starting from implementing the stateful layerful load balancer entirely in the data plane. So that way, you don't need to maintain hundreds of server-based load balancers. Instead, you could keep push this load balancer logic in the programmable switch, or you could even implement load latency congestion control algorithms like NDP. And INT is used for is one of the popular protocol for telemetry purposes. And even there are some exciting applications not related to network, something like using switch as a cache and store key value stores, especially the hotkeys. That way you could improve the throughput and latency. And there are other applications like improving the machine learning training time using by aggregating the by aggregating some of the operations and offloading these aggregation operations into the switches. And that way you could improve the machine learning training time. So these are some exciting applications that are built on top of programmable data plane systems. You can refer to these works if you're interested. Any questions so far before I continue? Right. So so in P4-16, P4 language is designed based on following one abstract data plane model that is PISA, which is also called, the abbreviation is protocol independent switch architecture, where you have these are the building blocks of the PISA. You have a programmable parser where that recognizes, you can tell the parser which packet header should be recognized. This parser is a simple deterministic finite state machine, where the transition between states is based on the fields in the packet header, field values in the packet header. For instance, you could program this parser to recognize Ethernet headers first, followed by, based on the Ethernet type, you can recognize the subsequent, you can go to a state that process VLAN, or you could go to a state in IP packet. And once you go into the IP based on the proto, you could go either TCP path or UDP path. And the core of this model is match action pipeline, where you can program these match action pipeline tables with flow rules, so that or table entries, where the packets which match with these entries and the action associated with that entry will be executed on the packet. For instance, you can realize L2 by programming the tables with in such a way that it would match on Ethernet MAC address and VLAN tag, and the appropriate action is forwarding to a particular port. Or in L3, it could be you can program the tables with appropriate destination IP, prefix entries, and then select the next hop, followed by changing the MAC address and TTL fields so that you can route the traffic to appropriate port. And finally, you have a deparser, which is the opposite of parser, or reverse of parser, which serializes the packet headers and then put it onto the interface or queue or application engine. And to summarize that, what I just discussed, where a parser would process the incoming packets and divide it into individual headers. And then these headers are processed in the switch pipeline, and actions are applied on the headers. Some actions include either drop or modifications to the header, or in fact, tagging some information that is also called metadata to the packet header. And then finally, you serialize the packet content along with these headers and then put it onto the interface. So that's the PISA in action. And here is a simple code snippet that you see on the left-hand side, where you can write a pass. The left-hand side shows the parser, where you could pass Ethernet header and then go either IPv4 path or MyTunnel path. It's a simple state machine. And on the right-hand side, you see the match action pipeline logic that is going to run the match action pipeline, where you first recognize if it is an IPv4. So then you go visit IPv4 longest prefix match table, and followed by forward table. So and when it comes to P4 specification, here is what it is expected from the vendor, where the vendor would supply the target's architecture model and the compiler for P4 language, and the user would supply the P4 program that defines how the packet should be processed. And this P4 program would be the input to the P4 compiler that is supplied by the vendor, and the compiler would generate target specific configuration binary, which again, this binary is loaded into the vendor's target, and program the match action pipeline with tables, external objects. Some external objects are some extra things that you want to apply in the packet. For instance, some extra functions like additional functions like include encryption, decryption, or using some CRC accelerator, or applying regex on the packet header field. So those are considered to be external objects, and the implementation is left to the vendor how they want to realize this. Whether they want to use network processors to implement these functions, or they use ASICs, or they use FPGAs, it's left to the network operator. Sorry, to the vendor. And the user would also supply a control plane. Actually, the output of P4 compiler is, in addition to the binary, it also automatically generates APIs. And these APIs would be used to interact with the tables that are programmed in the target, and also external objects. And also, if you want to send certain packets or examine certain packets, then you can send it to CPU port. So necessary APIs has been are automatically generated, and those are exposed to the control plane, so that the control plane at runtime would use those APIs to program these elements in the target at runtime. And so far, I've given the background on P4 and P4 target and how you program the P4 targets. So I like to go into one of the works that my group is currently looking at. One is, as you see, there are many components that actually define the final packet processing behavior, where you have a P4 program that where the P4 programmer would define how the packet should be processed, and what functions to be placed in the data plane. And there is a compiler that translates this P4 program to resource constrained hardware, or different software-based pipeline. And you have a control plane that listens to the network events and compute or compose flow rules at runtime, and then give those rules to the switch software that contains necessary SDK that takes the instructions from the control plane and program the data plane with associated flows. And you can see as we moving forward, you can see different elements here, and it is becoming increasingly complex. So the ecosystem is becoming complex, but all these are important to define the final packet processing behavior. To be more specific, any bugs in any of these components could eventually lead to incorrect packet processing behavior. For example, human-induced bugs while writing P4 program could cause mismatch between the actual intention and the actual implementation. Or a compiler that is sitting in the middle could translate part of the code incorrectly, or map this program constructs incorrectly to the underlying hardware. Or any bugs in control plane or switch software could lead to misconfiguration, especially if the rules are not programmed as expected, or then that could lead to incorrect packet processing behavior. To keep it short, you can see on the internet behavior, when programmer, the intention is to make the packet supposed to execute table A followed by action B. But if due to bugs possible that the actual behavior would be different, where it hit table C and action D. So here is to motivate further. Here is one concrete example where possibility of policy violation due to compiler bugs. Consider there is a firewall program that includes ACL and NAT, and a control flow graph of the P4 program would look something like this, where the ACL table has two actions, deny and allow, and NAT has again two actions, rewrite, which rewrites translates or rewrites the private IP to public IP. And if everything goes well, the compiler should translate this CFG to match action pipeline and place these tables in the switch pipeline, where ACL is applied first, where you filter the traffic based on the private IP addresses, followed by you apply NAT so that it will replace the private IPs with public IP. But if in case the compiler due to some bugs, if it replaces these, if it places the tables incorrectly, in other words, if the order is reversed, then if NAT is applied first and then followed by ACL, then the NAT would translate private IPs to public IP. And it is possible that there may not be necessary rules, essential rules from the ACL that's supposed to match on private IPs would match on public IP. And that could lead to security loopholes. So such incorrect table mapping would, due to bugs in the compiler, could cause incorrect packet processing and eventually lead to the policy violations, be it in security wise or in the performance side. Another possible example that I can, a possible bug could be in the switch software. It has been observed that whenever, usually typically TCAM is a limited resource. In other words, if there are too many table rules that wouldn't fit in the TCAM, then some of the rules would be kept in the switch software. Consider a situation where you have rules where R1 and R2 overlaps. In other words, a packet that match with R1 would also match with R2 in the ACL table. And now imagine that due to lack of TCAM, when there is no space in TCAM, then some of the rules would be mapped to kept in the switch software, and if not carefully place these tables, or if the split is incorrect between switch software and the TCAM, then it is possible that the high priority rule, that is source code matching with 443, would go to switch software, and low priority rule like source code equal to star would go to TCAM. And the packet that's supposed to match with the entry in the switch software would now match with the TCAM entry, and that could lead to the packet that's supposed to be allowed would be denied because the action associated with source code equal to star is denied. So this also again lead to policy violation because they could lead to break-in connectivity. So in short, bugs in any of these components that in the P4 ecosystem could lead to incorrect packet processing. And more importantly, these bugs would happen at runtime, may not be possible to detect it before you place these programs oftentimes. And in such situation, the question I'd like to ask is how to validate the packet processing behavior of the P4 data plane at runtime. This is important so that we could detect whenever the packet processing is not matching with the expected behavior. We like to know that and then find the cause and then fix the problem. But before that, first we want to detect whenever that such incorrect packet processing is observed. That is the focus of this work. And the key contribution is we developed a system called DBVal, Data Plane Behavior Validator, where it validates the actual packet processing behavior entirely in the data plane, which I'm going to cover in the next 10 to 15 minutes. Before I continue, any questions from the audience or the chat window?
I had a question. This is Preetham Patil here. not related to this particular topic, but are there any efforts to optimize these rules apart from validating their security or the correctness? Say, for example, you have a one flow rule saying 10.1.1.x and then another rule saying 10.1.2.x, and you could combine them to a single entry. Are there efforts to optimize such so that you are reducing the size of the tree as well as the size of the TCAM entries?
Yes, there is a decent amount of literature in optimizing these rules, especially using trie-based data structures. Is even that I can point you to the appropriate works which explore the space and come up with a small number of rules, but still keeping it deterministic but not probabilistic.
Thanks.
Right. So, so in this work, we first let the programmer to tell how the packet should be processed, which is nothing but the expected behavior, and we express the expected behavior using, we ask the programmers to write certain assertions that they want to check. These assertions basically classify the traffic or filter the traffic and define the expected behavior for that traffic. Followed by, we augment the program in such a way that enables you to keep track of the path or the actual packet processing behavior, and also execute these assertions on the observed behavior entirely in the data plane. For that, we augment the original P4 program and then give that input as to the P4 compiler. Finally, the P4 compiler would map this augmented program into the in the data plane. That part of it would left hand side, you would keep track of the path packet path execution, which captures the actual behavior, and assertion validation would compare the expected behavior that is derived from assertions with the actual behavior that we observed in the data plane. And if there is any mismatch, then the alert will be raised and informed to the in designing this system, there are two main challenges. First is how can a P4 programmer can express intended behavior. And
Praveen, I have a query regarding this.
Yes.
Yeah. So regarding the validation. So hi, it's Bidhov here.
Yes.
So I am a little bit confused over when does this validation actually happen. So is it like after we do the test, we construct all the information, we push the P4 code, and then we validate while the switch is actually handling packets, or we take a time off and validate and then push it to we ask the packets to go through it.
So this validation happens right in the data plane. It won't be sent. This information wouldn't be sent to any other or offloaded to an external entity. This validation happens in the data plane as and when the packet is going through the pipeline.
Okay, so in earlier cases there was no method, there was no easy way for validating it, and what we are trying to discuss is actually how we can have a better way of validating stuff without actually abstracting using more resources. Am I right?
Right. So the challenge here is maybe I will also talk about that in the coming slides. So the thing is, the main challenge is validating every packet means you either send this packet metadata that captures the actual behavior, the metadata captures the actual behavior, and then offload it to the external place. But the amount of resources that you need to offload this offload and then resources you need to send it to control plane and then store and then do the processing. The rates at which you process the packets in the data plane, that there is a trade-off there. While there is trade-off between the amount of resources that you give and also the coverage that you get when you do it in the data plane, how much coverage would you be covering every packet or on per basis, is the design choice that one can make while.
Okay. So actually, we instead of having a simulator or a separate testing scenario, we can actually inculcate that testing in this way so that we can reduce a lot of time and cost.
Exactly.
Okay, I got you. Okay. Please, I understood.
Now, the first thing is, how do we express the intended behavior? For this, we design an assertion language that has mainly two key constructs. First is the programmer would specify on the class of traffic or the subset of traffic on which the assertion should be applied, and the second key construct is what is the intended behavior in terms of which table it should hit and which action should be applied. That could be specified as a part in the assertion construct. To be more specific, consider this example where you have a policy saying that TCP connections that are initiated from external network should be denied by the ACL table. Then you could translate this assertion, or in plain English, the objective to an assertion that you see here. One, on the left-hand side, you see the traffic class or filtering the traffic based on TCP flags, and the ports on which it has arrived indicates the external network. And then the intended behavior or the expected behavior is to be denied by the ACL table, that it should hit this particular table and deny action should be applied. Given this assertion, our system would translate this assertion to appropriate P4 implementations and execute this assertion at line rate speeds, at line rate. Here is another example that you can see where imagine that you have a particular server. All the traffic that is coming out of that server should always have should always be encrypted. In other words, the source port should be 443, and the encrypted traffic should be allowed by the ACL table. Similarly, you could filter the traffic based on IP and the source port, followed by the path it should take in terms of table and the action that it should execute. We have designed an assertion language with a wide range of different operators, conditional operators, and a match on different packet header fields, also on metadata fields, and overall, this would enable to write a wide range of queries assertions, and test or you can validate most of the important traffic and deploy these assertions in the data plane using this syntax. For more details, you can look at the work that has been appeared in SOSR this year. Last year, 2020. And the second challenge is how do we keep track of the actual behavior that are processed by the data plane at line rates, and then followed by the validation of this actual behavior. For that, one approach is to take the packet's metadata, or capture the path information, a packet execution path information in the metadata, and then send it to control plane, and then validate in the control plane. But however, it has a lot of resource overhead because the rate at which we are talking is in the order of terabits per second. You have to allocate a lot of resources. So instead, to avoid such overhead, one idea is to make the expected or intended behavior accessible in the data plane. And for that, we translate these assertions into the data plane, and to capture the path, the actual packet execution or the path the packet has taken, we design a primitive that tracks the path the packet has taken, followed by validating the path the packet has taken and compare with the expected behavior that is expressed as part of the assertions. To be more specific, consider this match action pipeline where you have tables that are in green and yellow color, where the path that you are expecting is the green path, or the packet is supposed to hit green boxes. Imagine that packet was as expected till the first two boxes, but it went wrong in at the third in the subsequent stages. Then the validation module would match the path the packet would validate the path the packet has taken also in the data plane, and if there is any mismatch, then it would detect that mismatch and report as assertion failure and report it to the network operator or to the control plane. And for tracking packet execution path, we rely on one popular path profiling technique called Polaris encoding, where you could represent a P4 program as a control flow graph, a directed control flow graph. Since there are no loops in P4, it is easy to do so. And you label the edges in such a way that as packet traverses the tree or the table, where each node is representing a table and set of actions associated with the table. And as packet moves along the tree, then the label, the sum of the labels of the edges that it traversed would give you a unique ID. And that ID, in other words, also called BL code, would is unique to each path would be unique for each path in the CFG. To be more specific, you can see that a P4 program on the left-hand side for that has MPLS IPv4 tables. And on the right-hand side, you see the annotated P4 program with the appropriate update with appropriate BL codes that are added to the BL code variable as it traverses or if it executes that particular block or if condition. And when the program, as program traverses in the traverses the set of tables and actions, the packet would carry, the program would update a metadata variable, and at the end of the pipeline, you would be having a BL code that represents the path the packet has taken. And here is how we validate the packet execution path. If you see on the left-hand side is an expected behavior where the packet is supposed to take ADE, and there is a unique ID. There is a ID for that path. But if the packet takes a different path, which is shown in red color, which is ABC, then that mismatch can be detected by applying simple conditional operators in the data plane and detect and raise alerts when assertion fails. And how do we? And the next, and we realize this by translating the assertions that are written by the P4 programmer, and the DBVal compiler would translate this assertion to P4 implementations. We carefully design in such a way the filters are mapped to P4 constructs using if-else statements that you see in this box. And the assertion is nothing but the set of BL codes, possible BL codes that go through that particular node, ACL and DDoS in this particular example. And if the packet fall in that set of BL codes, then the assertion is success. If it is not, then there is a assertion will fail and then report to the controller. So to conclude this work, we summarize the work that we have done. This P4 ecosystem is becoming complex and there is possibility of bugs. And if even a single bug could cause mismatch between the actual behavior and the intended behavior. And this work the main objective is to validate the packet execution or the actual packet execution path, and detect whenever there is a mismatch between actual behavior and expected behavior, and report to the network operator. So before I move on to next work, any questions on this? So leveraging the programmable data plane features, there has been many works that build based on the idea of data-driven closed-loop systems, where the main objective of this closed-loop systems is to improve the performance of the latency and by leveraging the programmable data planes. To be more specific, in many of the systems you have they monitor the network state in terms of related to link stats, flow stats, or path statistics. Sometimes even you would collect statuses that are required to detect DDoS and provide this information to a centralized controller or analyzer, where you have different applications related to routing, security, management, and after doing the complex processing or sophisticated analysis, they would come up with certain actions that are related to, could be perhaps traffic engineering or related to security, or be it rate limiting some of the traffic to meet some metering requirements. So it sometimes you execute these closed loops either invoking a centralized component like HDN controller, or sometimes oftentimes P4 enable you, given its programmability, it would enable you to execute this all three functions: monitoring, analysis, and action entirely in the data plane, so that enables fast control systems. Of course, the assumption is that the kind of operations required for analysis should be amenable to be implemented in the source constraints or P4 constraints in terms of operations that is allowed. Something like, if you look at the P4 program or the underlying programmable data plane, they would allow you to do simple addition, arithmetic operations like addition, subtraction, or left shift, right shift, XR, or sometimes, but it won't allow you to do multiplication, division, certain operations. So which are sometimes lead to, there is a trade-off between the number of cycles to execute those operations and also the accuracy that you get when you execute those. So approximate data structures is another way to capture to perform those operations. I'm not going into it, but in general, this is the high-level idea of monitoring, analysis, and taking action entirely in the data plane, so that you could make decisions quickly. And given such high programmability, it also increases the attack surface. Some potential threats could be related to DOS, evasion, poisoning, bad QoS. Let me spend some time and explain what are those different attacks, possible attacks. So one possible attack is if an attacker somehow knows about the logic that is running inside the switch, he could exploit that logic and craft malicious traffic that trigger or trick the logic that is running in the data plane, entirely in the data plane. Or sometimes it is also possible that an adversary on the compromise which could send spoofed traffic or manipulate the original traffic, so that it could eventually generate fake data plane signals. And if the switch blindly relies on these signals that are coming from adjacent switches, then that could lead to performance degradation, significant performance degradation. And even worse is to a compromised HDM controller or the switch operating system or a switch SDK drivers, where you program the forwarding plane by modifying register state and table rules. And if these are somehow manipulated by an adversary that is sitting in the middle, it could lead to either rerouting traffic to a wrong path or congested path or other security issues would pop up. And eventually, there are potential threats could be the denial of service, or evasion being detected, or poisoning the network statics that you collect, or bad QoS by sending traffic to an over and on path. So to be more specific and motivate further, some possible example attacks one is triggering CPU expensive paths in these fast control loop systems, especially that invoke control plane CPU for certain packets. If you trigger this path frequently, then that could cause loss on the switch CPU. And another way is to trick the system by generating fake data plane signals so that it could pick the wrong path. That could lead to performance degradation in terms of latency, performance degradation, be it throughput or latency. And an adversary who is sending malicious traffic could corrupt the in-network data structures like compact data structures like Bloom filters or sketches that are mainly used for different network management purposes, be it network monitoring, security, or traffic engineering purposes. And that could lead to bad QoS or avoid from being detected by some of the intrusion detection systems. And also another type of possible attack is saturating the limited memory that is available on the switch. Especially, you can trick the system to install some rules for malicious traffic, which are supposed to be where these resources are supposed to be used for legitimate traffic. If you use these limited resources for malicious traffic, then that could cause DOS on the network infrastructure. So here is one concrete example, one recent system that use switch as a catch and improve the key value that improve the throughput in key value store system. Here you see a system where you have on the left hand side clients that are generating get key requests to the storage servers on the right hand side of the switch, and you expect it, and the clients would receive the reply to and the reply would go to the switch. Now, if that key is requested for greater than threshold number of times, that is also user defined, then it would be better to keep this key value inside the switch so that you could avoid an additional hop latency at the server, and the switch would be acting now as a catch. So based on this, to improve the performance in terms of throughput and latency, you could configure the switch to keep these hotkeys and associated values in the switch, so that once a particular key exceeds is requested for more than threshold number of times, the switch would generate response and then send it to the client on behalf of the key value storage servers. By doing so, you could one thing is that P4 data planes are much faster, and so that you could improve the throughput in terms of in terms of queries per second, key value pairs, queries per second, and also the latency would go down significantly. So this is the key idea of this netcache, using switch as a cache. Also, the term they use is netcache. But here is one memory saturation attack on netcache system possible, where if the attacker can would generate requests, too many requests, where he could generate too many distinct hotkeys. In other words, keys that exceeds that particular threshold, and in such situation, the controller would install the keys that are associated to the adversaries or the based on the adversaries, and that if there are too many such requests, then the resources that are supposed to the resources like TKM and STM that are supposed to store the key value pairs for legitimate users now be populated or occupied by keys of keys that are generated by the key requests that are generated by the adversaries. That could eventually lead to increase in the response time. So there are many. This is just one example, but there are many challenging research problems given the resource constraints. How do we detect such security issues and also mitigate such issues and what are the mechanisms to be placed to avoid such security issues. It's still, there are many problems and still open research area, so that this security by design, especially in the resource constrained hardware, is important, and there are many opportunities to work on this problem. With that, I'd like to conclude my talk and like to take any questions. So here are some great resources to continue working on P4. These are they're very, to give you a kick start onto how to get started with working on real systems using P4 and build a test bed, or to learn more about this programmable data planes and P4 ecosystem.
You'll be sharing the slides with us, if it's okay?
Yes, I already shared the slides with the host, so I think the host would make this available to all.
Slides would be available on our website.
Okay, thank you, Ashley. Got it.
I had a again slightly unrelated question, Preetham Patil. On the apart from the flow definition rules and the packet header processing rules, what are the predicates available for controlling the queuing behavior within the switch?
Good question. So I think as per the P4 spec, the scheduling part is closed, in other words, not programmable. So it is left to the operator what kind of scheduling mechanisms at the interfaces and how you want to schedule packets in the queue. That is left to the network switch vendor. So it is not exposed or not programmable by a P4 programmer. At the moment, it is considered to be an closed function.
Oh, so something like a Codel or AQI, AQM is not out within the scope of P4, is it? Like P4 runtime? I mean.
Yes. They're not, at least from that is from the vendor side, but there are some research work that approximate the scheduling behavior in the match action pipeline. So especially you can tag the packets with the information in the ingress and egress pipeline, so that that could be used while scheduling. And I think I'm not expert in that, but I can refer you to some approximate QE scheduling mechanism that has been becoming very important. I think also in the network slicing side, there is this recent work trying to offload, trying to implement some queue scheduling algorithms using limited queues that are available. At the moment, for each interface in the Stofino switch, they have about 8 or 10 queues. But for network slicing, like kind of applications, you may need more than 100 queues to enable QoS for different tenants or applications. So how do we map this hundreds of queues, virtual queues, to the actual hardware queues is still an open area, at least in the P4 programmable data plane side.
Okay, since there are no other questions, maybe let me hog the time. So what is the currently the most easiest way to work on a hardware P4 device?
Easiest is one is there are many different P4 targets. If you are looking at just to implement the prototype, but not care much about the performance in terms of packet rate or the latencies, then I would say starting with the software switch model called DMV2 and P4, which also I've given here, P4 language tutorials, would be a good starting point. And the next step could be either you could start working on software-based high-speed packet processing units, like something like DPDK, eBPF, or SmartNICs that are coming from vendors like Netonome that supports P4 right from the start. So SmartNICs are even more considered to be give you packet rates at 40 gig to 100 gig. Even today, the recent SmartNICs can support up to 200 gig per port. Those are the other options that are available. On the software side, eBPF and DPDK, and the SmartNIC side, Netonome. And when it comes to switch router that can process traffic at more than 10 terabits per second, there is this Rufino switch from Intel that we managed to get it to India, and we can also work on their SDKs and SDEs and deploy some of the that is the third option.
Thank you.
So, Praveen, so how are you doing your research on this? So, like the implementation part and testing part? What are you using?
So we are working on DMV2 and real Rufino switch. We have implemented these modules on both platforms. One high performance platforms and another for the testing functionality purposes. We are using DMV2, and we have plans to also extend this to other platforms like, software-based packet processing can be, you can download their GitHub open available GitHub repos. We also have SmartNICs, SmartNICs to try out. They're a bit flexible compared to Rufino switch, more flexible. So,
okay, so all of them are actually available online. No, we can just try it out, download and play with it.
Yes. So except of the actual hardware, Neton, SmartNIC, and Rufino switch, the rest are available online. Yes.
Thank you.
Thank you, Dr. Praveen, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the web page. Thank you and have a great evening.
Thank you so much. Thank you for giving me this opportunity, and looking forward for potential collaborations. Thank you. Bye-bye.